Hi there, Jim Caffey here with the Essential Cosmic Perspective book. This is Chapter 10 over Other Planetary Systems, the New Science of Distant Worlds. So our goal for this part is going to be how do we detect planets around other stars? Well, here's a picture that someone took of some interferometry, which you've already learned by now, of some planets orbiting a star where they have tried to cancel out the image of the star itself to reveal the image of the planets around it. We see 4 planets, maybe 5 around it. So why are extrasolar planets difficult to detect? Well, a sun-like star is about 1 billion times brighter than the light reflected from its planets. And planets are so close to their stars that relative to the distance from us to the star, this is like being in San Francisco and trying to see a pinhead 15 meters from a grapefruit in Washington, D.C. So pretty tough stuff. And during this section, we're going to talk about a friend of mine, a colleague named Dr. Sarah Seeger, who is a planet hunter that looks for these kind of things. So there are 2 different types of measurings we can do to find planets around other stars. We can take direct pictures or spectra of the planets themselves, and a spectra is splitting the light up into its component colors, and we get information from that. We'll go more into that here in the future. Or indirect means by measurements of stellar properties revealing the effects of orbiting planets. So we can have a gravitational tug where the planet itself is tugging against the star, and we see that star move and wobble. So the Sun and Jupiter orbit around their common center of mass, and the Sun therefore wobbles around that center of mass with the same period as Jupiter. So that's one way. The Sun's motion around the solar system's center of mass depends on the tugs from all the planets, and we know that astronomers around other stars that measure this motion could determine the masses and orbits of all the planets. So we know that. And so we can detect a planet's measuring by the change in a star's position in the sky. However, I'll clue you in on this. These tiny motions are extremely difficult to measure. They are nearly unmeasurable, pretty much. So that's not a good way. So we have another way called the Doppler Technique. And this is where we measure a star's Doppler shift, and it can tell us the motion towards and away from us. Current techniques are able to measure motions as small as 1 meter per second, which is basically a walking speed. We can do that with the spectra and the Doppler technique. And so the first extrasolar planet was discovered by Dr. Jeff Marcy, a colleague of mine in California, in 1995. He found Doppler shifts of the star 51 Pegasi indirectly revealed a planet with a 4-day orbital period. That's extremely close considering Mercury's orbital period is 88 days around the Sun. So this very short period meant the distance had a small orbital distance. And this was the very first extrasolar planet to be discovered around a Sun-like star by Dr. Marcy. But another way we can do this is with transits and eclipses. So a transit is when the planet crosses in front of the star. Just like my research that I did in my program at Missouri State University, where I looked at stars that pass in front of each other and had eclipses, this is similar to that. This effect, the transit, reduces the star's apparent brightness and tells us the planet's radius. Sometimes an eclipse is caused, and the planet behind is passing behind the star, and that can also be detected. So we launched a space mission called Kepler. And so Kepler was launched in 2008 to begin looking for transiting planets. And to date it has found over 500 transiting planets. And a colleague of mine at Missouri State University is on the team that looks at this stuff. It's designed to measure a very small decline in brightness when an Earth-massed planet eclipses a Sun-like star. And this mission has far exceeded our expectations to this point. Other planet hunting strategies is gravitational lensing. A mass bends the light in a special way when a star with planets passes in front of another star. And we can see gaps, waves, or ripples in the disks of dusty gas around stars that can indicate the presence of planets. So we have learned that direct starlight is billions of times brighter than the starlight reflected from the planets, making imaging extremely difficult. And a star's periodic motion detected through the Doppler shifts tells us about its planets it may have, and the transiting planets periodically reduce a star's brightness on an orbital scale. Now we'll look at the nature of planets around other stars. What properties of extrasolar planets can we measure, and how do these extrasolar planets compare with planets in our own solar system? So here we can measure the Doppler effect of a star and its planets or transits and the eclipses, and put it into equations you've already learned from Galileo, from Newton, and Kepler with their laws to get the planet's density and orbital period and mass. So what can we measure? We can measure the orbital period, the distance of the planet away from the star, and the shape. We can also measure the planet's mass, size, and density, and its atmospheric properties, if any. We cannot measure an exact mass for a planet without knowing the tilt of its orbit, because Doppler shifts tell us only the velocity towards or away from us, not side to side. And Doppler data gives us lower limits on masses anyways. So here is a system called the Kepler 11 system. The periods and sizes of this sixth known planet system can be determined using transit data. And on the right hand side here you see the light curves, which we call them, where the planet dips down and eclipses the star. Similar to my research at Missouri State. Using mass, then we can determine, using the Doppler technique and the size, we can calculate density of the planet. Is it a Earth-like planet or is it a Jupiter-like planet with the density? So how do extrasolar planets compare with those in our own solar system? Most of these detected planets have orbits smaller than Jupiter. The planets at greater distances are harder to detect with the current techniques, even with Kepler. And the orbits of some of these extrasolar planets are much more elongated and have a greater eccentricity or more elliptical orbit than those in our solar system, which are pretty circular. So results from Kepler indicate that planets are common, and small planets greatly outnumber the larger planets. So there are some Earths out there that we can detect. So all of these that we have been able to detect so far are the mass of Jupiter and Saturn, Uranus and Neptune, just a couple known to be the size of Earth and Venus. And this is just simply because of the detection ability of Kepler to be sensitive enough to determine the detection of an Earth-like system. So some extrasolar planets have highly elliptical orbits, and these planets show huge diversity in the size and density. Some massive planets, however, called hot Jupiters, orbit very close to their stars and make them that hot. So we learned that orbital properties such as period, distance, and shape can be measured. The planetary properties such as mass and size can also be measured, and also the atmospheric properties such as temperature and composition can also sometimes be measured. Planets with a wide variety of masses and sizes are found by Kepler, and many are orbiting close to their stars and with larger masses. And now we'll finish up with the formation of other planetary systems. Do we need to modify our theory of solar system formation with the solar nebula theory? And are planet systems like ours common? So revisiting the solar nebula theory, it predicts that massive Jupiter-like planets should not form inside the frost line at about 5 AU. The discovery of hot Jupiters has forced the re-examination of this nebula theory, and planetary migration or gravitational encounters may explain these hot Jupiters. A young planet's motion can create waves in a planet-forming disk, and these models show that matter in these waves can tug on a planet, causing its orbit to migrate inward. The close gravitational encounters between the two massive planets can eject one planet while flinging the other one into a highly elliptical orbit. And this is called an in-body simulation, where more than two bodies are in play. We have multiple planets and one massive star, and it's not conducive for multiple objects to be going around it. Multiple close encounters with smaller planetesimals can also cause an inward migration, and resonances may also contribute to this. There seems to be a much greater variety of planet types than we find in our own solar system, and this includes gas giants with very different densities and water worlds around them. So, modifying the nebular theory, we can say that observations of extrasolar planets have shown that the nebular theory was incomplete, and effects like planetary migration and gravitational encounters might be more important than we previously thought. So, is a planetary system like our own Earth common? We think they are, but this is yet to be seen. So our final slide here says that the original nebular theory cannot account for the existence of these hot Jupiters, and that planetary migration or the gravitational encounters may explain how Jupiter-like planets moved inwards in the first place. So are planetary systems like ours common? We don't know yet. The answer is coming soon. Thanks for watching.